Okay, so listen now. I showed you guys some calculator stuff yesterday. And quickly, I don't want to, I think you've got it, right? All you have to do, if you want to do any kind of arithmetic, division, you can exponentiate them, take them to powers. If you want to do anything with complex numbers and let the calculator simplify it for you, it will do this. This is really, really handy. This is an absolutely great trick to use on SAT tests, or, because you can. And so it gives you a decided advantage if you know how to do these things when you go into these big tests where they allow you to use a calculator. So all you have to do, remember, is go to mode, and near the bottom, you just change it from real to imaginary mode, A plus BI mode, right? Yeah. There's another imaginary mode that it's polar imaginary coordinate, or using the complex numbers expressed as in polar form. Not going to do that this year. That's for future. You want the one, the A plus BI one. Now, a couple things about that though. When you're not, if you're not wanting imaginary numbers, I would recommend you take it out of there. Like for example, there's going to be a second quadratic formula assignment where I'm going to ask you to do stuff that's really kind of almost more real world stuff, where I'm going to ask you to find only real solutions. And the instructions will say if there are no real solutions, meaning if they're imaginary, you just enter an N, meaning no real solutions. A lot of times in real life, we only want the real solutions. And so if you're in that mode where you're only looking for real ones, put it in real mode. The reason being, if you don't, if you have it in float mode, which you normally will, and you have it in A plus BI mode, sometimes it's hard to tell if it gave you back an imaginary number or a real number. Remember, we did a couple examples yesterday. Well, how about if we just do like that one, right? So if I put in, and also remember, you can't use the fraction template with imaginary mode. It won't work. You have to just use parentheses instead. So if I put in the square root, oh, there it is.
I don't like how.
Square root of 2 times I. Remember, I is just behind the decimal point.
Isn't it plus I?
It is plus I. Thank you. Plus I divided by, and I got to put the whole denominator in parentheses, right? Divided by 2 plus 2 times square root of 2 times.
Wait, do you have to put this?
I don't think you need the times. If I do this and I hit enter, see, here's the problem with this. Look what it does. It gives you this big long decimal, and then if you don't recognize, clear off to the right, it's going to give you minus some other big decimal times I. So this is A, that's B, and I is clear over here. But you see the danger of that. Sometimes, you might look at that and just see that big decimal and take that to be a real answer, which it's not. And that's a pretty common mistake. Trust me, it happens a fair amount. So once again, if you're just looking for real answers, you might want to get out of that mode. The other thing you might want to do is, like on the assignment, I'm going to ask you to round all your decimals to the nearest thousand. So you round them to 3 places. The other thing you could do that's also pretty slick, that helps you out, is to go down, maybe, I can't remember if I showed you this or not, you go down to float.
Yeah.
I did show this to you. So you go to like float 3. And then if I repeat that calculation,
why is there a dash and then a period? That's because they're 2 separate numbers.
right, it's not a dash, it's a minus sign. See, that's A
I
minus,
got you.
see,
Yeah.
A is 0.471,
Because
B
you
is
can't
negative
combine.
0.167. Okay, now that's also pretty helpful. Then you can see the I better on there, right? But then the danger of this is, if you leave it in float 3 mode, you got to remember to kind of undo these settings when you use them, because now if you leave it in that mode, it's going to round everything whether you want it to or not. And so that could cause you to input some wrong answers, right? So when you're done, just turn the stuff off. Questions in any of that?
No.
Does that make sense?
No.
Okay. So then what about stuff like this? If people were questioning, how do you these are hard. Not really hard, they're just inconvenient. But you do them the same way you would do any other complex number quotient, right? We're just going to multiply top and bottom by the complex conjugate of the denominator. And remember why that works. Remember why this strategy works for us is because when we multiply conjugates, and we'll talk a lot more about these patterns in chapter 6, but when we multiply conjugates and we FOIL them out, remember that the O and the I terms always cancel out, right? That's a property of conjugates. And so really when you FOIL them out, all you have to do when they're conjugates is first times first plus last times last. And for complex numbers, that's a big advantage to us because those are the two terms that are going to end up with no i's in them, right?
Yeah.
I'm going to get an integer and then an integer times I squared, which is a -1. It's only the middle terms where we get the i's, and those drop out when we multiply conjugates. So that's why we do this. That's why this strategy works. So if I multiply the top and the bottom by the conjugate of the bottom, let's just quickly walk through that math so you can kind of see the arithmetic. So first times first is pretty easy. That's just 4, right?
Yeah.
And I don't have to do the middle ones. Last times last. Now what's that? I've got 2 radical 2i times -2 radical 2i. So what we really have to look
2
at here
times
is
4.
what is 2 times the square root of 2 times 2 times the square root of 2?
4 times square root of 4.
Okay,
Which is
good.
4
Now
times
we can organize those any way we want to, can't we? If we're multiplying 2 times the square root of 2 times 2 times the square root of 2, the way we would choose to group those, because we're just multiplying 4 factors together. You choose the order, right? Really, you're just squaring the 2's. 2 squared is?
4.
Yeah, 2 times 2 is 4, good. And then you're squaring the square root of 2's.
So 2.
2. So I just get 4 times 2 is
8.
8, okay?
What about the negative sign?
And then you get a negative sign, don't you? Right, because one of them's negative. So we're going to get a -8 I squared, but the I squared changes it to a positive. Okay, so the bottom's easy. The bottom's always going to work out nicely to be an integer. In this case, we just get a 12. Top, we have to go through and do the whole FOIL process. So square root of 2 times 2 is just 2 times the square root of 2, right? Outside product, square root of 2 times -2 square root of 2i. Well, in that case, which two factors would we multiply together first if we're doing those two guys together? Square root of 2's, right? Square root of 2 times square root of 2 is 2, times -2 is -4i, right? Okay? Inside terms, easy. I times 2 is just 2i, right? And then the last one's pretty easy too. I just get an I times that last term. So there I would multiply which factors together? The i's. I times I is I squared, which makes -1, times -1 times -2 times the square root of 2 is just positive 2 radical 2.
Yeah.
Right. And then all I do is combine like terms. I've got a common denominator on the bottom, so I'll gather up all of the real terms together, right? 2 square root of 2 plus 2 square root of 2 is what? 4 square root of 2. Is there any confusion about that?
What happened to this I squared?
Well, we got rid of it. I squared is -1, so that's what changed that sign to a positive. Okay. Now remember this. Here's a good way to think about this, because sometimes people try to remember too many rules in their mind, and it gets confusing. This is the very same rule that you naturally use when you're multiplying variables. If I asked you what 2x plus 3x is, you'd tell me 5x, because you have 2x's plus 3x's, right? If I have 2 times the square root of 2 plus 3 times the square root of 2, I would just get 5 times the square root of 2 for the same reason. I've got 2 square roots of 2 plus 3 square roots of 2 would make 5 of them. Anytime that you are adding up terms with coefficients like that, and a coefficient just means a number out in front that's being multiplied by something, right? So in this case, the coefficient of the square root of 2 is 2. In this case, it's also 2. Whenever I add up terms with coefficients, you just simply add the coefficients. That's all you're doing. You're adding up numbers of something, right? Or subtract, same deal. Make sense? Okay. So then this is the real part that we get. And then if I add up the imaginary terms, I get -4i plus 2i is just -2i, right? And now I ultimately want to write this in standard form, right, for a complex number, which is the real part plus, separately, the imaginary part. So what do I do to this fraction then? Right now it's got a common denominator, so they're not separated. Yeah, just separate the fractions. Each numerator keeps the 12, and then we can reduce separately. So I get the 12 in the first fraction, reduces 4 over 12, reduces to 1 over 3. In the second fraction, the 2 over 12 reduces to a 1 over 6. And so that's my final answer. And you can put that I in the numerator if you wanted, that's fine. Okay. Make sense?
You're gonna put those together and have like a.
No, this is how we'd write it, because that's A plus BI.
Oh, okay. never
Okay.
mind.
And so when you do it on your calculator, you know how you just showed us?
Yeah.
Those decimal answers, could you convert them to fractions?
Okay,
to
yeah,
get
now,
that?
you can convert them to fractions, but the TI-84s, as nice as they are, they're a little bit limited. They won't convert them to square roots, right? And so now, there are some calculators that do. The TI-89, which is the one I prefer, does that, and then the TI-Inspires also do that. You don't need to run out and get those, but, I mean, there literally may be a point when, if you're gonna go be an engineer or mathematician or a physicist or something, there may be a point where you might want to upgrade when you get to college. For now, I don't think you want to, because you can't even use those calculators on a lot of the high stakes tests that you're going to take. But in college, when you get, after you've done the SAT and all that stuff, if you're in one of those areas, you might want to consider that. Okay? And maybe they'll change by then. But that's your answer. Yeah. Okay. So let's see. Yeah. So moving on. So what about something like this? People are looking at these, and these look pretty dreadful. I agree. But what I want you to remember about this, you can make these a lot simpler. Whenever I have a quotient of quotients, meaning if I have a fraction on the top and a fraction on the bottom, all nested together in one big fraction, we always have the same strategy. The strategy is simplify the top into one fraction and the bottom into one fraction, and then flip and multiply. It's always easier to do products than quotients, isn't it? Right? So we could rewrite this from the very beginning. I have an option here. I could just simplify the bottom if I want to, right? And then flip it, right? Except if I do that, really I'm going to be kind of undoing some work in a way if you think strategically about this. And a lot of math is thinking strategically. If I simplify this bottom quotient, aren't I going to end up with i's on the top and real numbers on the bottom?
Yeah.
But when I flip it, I'm undoing that hard work, aren't I? I'm putting the i's back on the bottom again. So in a way, doesn't it make more sense to flip it first and then simplify second? Right? So I could rewrite this as negative 3 over 1 times the reciprocal of the bottom, right?
Oh.
Times negative 1 plus 4i over negative 2 minus 2i. Right? And all I have to do with that, that's an easy product. I just distribute the negative 3 through the top, right?
Yeah.
So I end up then with positive 3 minus 12i over negative 2 minus 2i. And I could even, well, no, I guess I'm stuck with that, aren't I? And that's one like you've done. That's one of the ones like from the first assignment. Now we have to take care of this, but at least it's just one quotient. I would just multiply top and bottom by the complex conjugate of the bottom, right? Okay? And so it's not so bad.
-2 plus 2i.
Yep, negative 2 plus 2i, right? But does that make sense that you'd want to flip first?
Yeah.
Okay?
So where would you multiply?
Well, because we'd like to make this as easy as possible. The hard part of these assignments you've been working on, when you're doing arithmetic with complex numbers, the hardest part is doing a quotient, right? So why not simplify this down to a single quotient? So you only have to do the quotient once, right? I mean, you could distribute the 3 afterwards. It's not going to make that much difference. I would just do it this way. Okay. If we could have factored out a constant from the top and the bottom and reduced this thing, that would have been nice to do, but we can't, because there is no common factor of 2, 3, and 12 other than 1. But if there had been, we could have done that also. Okay. All right. Why did I have that? I don't need that one. I don't think I need that one. Okay, this one. Okay. Now I don't know how many people have gotten into the quadratic equation assignment, but it's easy. I mean, it's easier. It really is. Now you can start to see that dreadful test that you almost had to have included in your first semester, where you had to complete the square to solve a lot of these equations. That's kind of a dirty trick on my part, I suppose. A lot of those questions are going to be a little easier now, aren't they? That you have the quadratic formula. Finding the solutions is you just plug and chug into the formula, right? Okay, but what about something like this?
AJ Thompson, come to the office.
Okay, what about something like this? Now, if you're just trying to get decimal answers, you could easily plug, what are we gonna do first of all? Regardless of what we do with the fractions, what do we have to do to that equation before we? Good, we gotta get everything on one side and A must be positive, right?
Yes.
So we would move everything to which side?
To the left.
Alright.
To the right, good. Because negative 1/4 is bigger than negative 3/4, right? Agreed? You could, sure. You could multiply by -1 and go the other way if you want to also, that's fine. Okay, but, so you'd agree we'd have to push everything to the right this time, right? So doing that is gonna be a little bit of a pain because we've got all these fractions to deal with. Now, if we are doing this on a calculator and we're getting decimal answers, you might say, well, that's not such a big deal because I could just add up all these fractions on a calculator and then as long as I get fractional answers, which my calculator would give me, I could put those in for the values of A, B, and C into the quadratic formula on my calculator and it'll make short work of that, that's fine. But this is from the part of the assignment where you have to provide exact answers. So I don't want decimals, I want exact answers that are going to include square roots. And so you can't do that. You have to go through this by simplifying the quadratic formula sort of manually, right? That's gonna be a real pain, chasing all those fractions around. So what do we do?
Create a same denominator.
Okay, good. This is a classic case where you wanna clear the fractions, right? Clearing the fractions, and I keep harping on that, but it makes this problem so much easier. If you ever have big expressions where everything is a sum of terms, terms that are being added or subtracted, you can always clear the fractions. It gets a little more complicated when you have products in there also. And the trick is, honestly, all you have to do is just multiply the fractions first, so you expand it, so you get a sum of a bunch of terms. Multiplying fractions is easy. That's just multiply straight across. That's no big deal. It's when you get to the adding and subtracting part anyway that it gets really complicated. We'll see more examples of what I'm talking about now in the next chapter. But for now, we're just starting with stuff like this. So we would clearly want to multiply through by the least common denominator, which is 12. 12, yeah. Okay, so if we do that, if I multiply through by 12, and you're going to get some like this on the assignment. Okay, if I multiply through by 12, somebody walk me through the first term. When I distribute this 12 to the first term, how do I do that most easily?
Divide.
Okay, you're right. Because I know, remember, when you're clearing fractions, you've handpicked that number out in front, that 12, to be a number that all the denominators divide into evenly, right? So you can always pre-reduce and then multiply.
So wait, are we dividing them?
Divide the 12 by.
Exactly. So what you want to do, you'd rather divide the 12 by 4 first and then multiply by 3, right? So you're dealing with small numbers.
Yeah.
If you multiply straight across, sometimes you get big quotients that are hard to deal with.
Alright, so we divide.
So you reduce first and then multiply. Here's the way I like to show this. It's not a big deal. You don't have to do this, but if you did want to kind of keep track of this on your own, here's how I do it. I say 12 over 4 is 3, and then 3 times -3 is
-9.
-9.
Whoa.
Okay, see how that works?
Okay.
Do that one
Okay, 12 over 12 is
12 over
1 times -7
-7.
is -7.
Okay, that makes sense.
Wait,
Okay, right?
yeah, how
Okay.
did you get the 12?
Yeah, this is good. This is good.
Mr. Olin,
Yeah.
Do you get
could
it?
you multiply it all by -12 and then get rid of it?
Well, you could, yeah, you absolutely could. It'd be fine too.
Wait, okay, so how did you get the 12 and then the -7?
Because we're always going to pre-reduce. We're going to say 12 over 4 is 3.
So think
Multiplied
there's
by
a
the
1
top
and
is
a
made is,
Okay, so 12 over 4 is 3.
Yep.
And then what do you do next?
then you just multiply that by the numerator.
Okay, so for the next one, you do 12 over 12 is 1.
1
And then you,
times 7.
does that work for all of them?
Yep.
So,
Why didn't we get taught this in elementary?
Well, when you're clearing fractions, it does, because they always divide in.
that is so easy.
Why didn't we get taught this in
This
elementary?
is so.
Okay.
It's like we make it harder.
Okay, so now listen, let's wrap this, just a couple little issues here. So what about this guy? This is easy, right? This isn't a fraction. I just distribute. Don't even need to do it there. Then over here it's the same deal. 12 over 4 is 3 times -1.
-3x squared.
right? 12 over 4 is
Three.
3 times negative 1. 12 over 2 is 6 times negative 1, right?
Wait, what if it doesn't go evenly
No, okay, but,
Always?
okay, no, it won't, listen please, okay, it won't, in just a random problem, it wouldn't always work like this. But, how do I say this?
You're
Let me,
getting
let me choose my words very carefully, because I want to make sure this doesn't confuse you. When you're clearing the fractions, it will always work, because the number you're picking is a least common denominator, meaning a least common multiple of all the
So
denominators.
it'll always work.
So it always works clearing the fraction.
But you
Yes.
have to have at least common denominator.
Right, exactly.
This is so
Yeah.
cool.
Okay, and then from here, I can probably just leave it to you from here, right? All we do is just add the terms to one side, put them in the quadratic formula, and you're set.
So is there a point where like the numbers would be so big that it'd be easier just to do the fractions?
No, in fact, I would say as the numbers get bigger and bigger, this becomes more important to do, because then the fractions get more daunting, yeah. So you definitely want to, the worse they are, if they were really small fractions, maybe you could just add them and subtract them more easily, but if we get different denominators and as they get bigger, that's a real pain. Okay, make sense? Any other questions? 20, hang on, I gotta make sure we get the right one. I don't wanna go barging in on somebody.
I